Okay, let's dive right in. For the next month, we're doing things a little differently. We're not just treating you as Year 10 students, we're treating you as young professionals on a 4-week trade mission. We are going to completely bridge that gap between textbook science and the actual hands-on skills that literally keep the modern world running.
Here's a quick look at our briefing overview today. We're going to cover chemistry in the trades, the logistics of your 4-week mission, how to use your scientific logbook, mastering variables and methods, and finally, nailing the discussion section.
Starting right off with Section 1, Chemistry in the Trades and its real-world applications.
You know, chemistry really isn't just about test tubes and lab coats. It's actually the exact science that plumbers, sparkies, builders, and mechanics use every single day to get the job done right, keep people safe, and prevent massive structural failures. Now, you've got an absolute arsenal of 8 distinct experiments to choose from, and every single one links directly to a real-world trade and the actual money-making science behind it. For instance, Experiment 2, cement setting, explores exothermic reactions. That is absolutely crucial for a bricklayer who needs to know exactly how fast a site will dry. Or take Experiment 5, acid-base reactions. That's the exact chemistry a hairdresser uses to safely dye hair or an industrial cleaner uses to neutralize chemical spills. You have 8 real-world problems. The choice is yours.
Okay, moving on to Section 2, let's talk about the logistics of your 4-week mission. Let's look at your weekly rhythm. Your objective is crystal clear here. Out of those 8 options we just talked about, you must select and complete exactly 4 experiments over the next 4 weeks. That means you're tackling 1 fresh experiment and 1 fresh trade application every single week. Now, this breakdown is absolutely crucial for your weekly routine. Listen closely. During your double period, you are going to get hands-on. You'll execute the practical experiment, whether that's crushing effervescent tablets to test reaction rates or burning fuels to test efficiency. And you'll actually start your full write-up right then and there. Then you're going to use your following single period to finalize and polish that documentation. So do the science in the double, perfect the paperwork in the single. Simple as that. Which brings us to Section 3, the scientific logbook. This is your master record. Look, every great tradesperson keeps a meticulous record of their work. Your logbook is where you'll prove that you truly understand the chemistry behind the tools. You're going to complete a full write-up in this logbook for every single one of your 4 chosen experiments. So, what goes into it? Your logbook is structured into some very specific sections. You'll start with your title, which has to be formulated as a question. Then you've got your introduction and your if-then hypotheses. For example, if we change the temperature of the water, then the reaction will speed up. You'll map out your variables, list your materials, step through your method, and record your raw data in the results section. Just the numbers there, no explanations yet. Finally, you'll wrap the whole thing up with a heavy-hitting discussion and conclusion. All right? Section 4, variables and methods. Let's set the rules for how we do this. Getting your variables right is honestly the difference between a messy guess and actual science. The independent variable is a thing you actively swap out or change on purpose, like choosing cold water versus warm water. The dependent variable is the reaction you're observing. It's what you measure with your stopwatch, your thermometer, or your pH paper. And remember, your controlled variables are absolutely everything else that you must keep exactly the same to make sure it's a fair test. When it comes to the method, you can't just copy and paste. You've got to write a numbered, step-by-step procedure entirely in your own words. The golden rule here? Clarity. You need to write it so clearly and simply that a Year 7 student could walk into the lab, pick up your logbook, and do the experiment exactly as you did it without having to ask a single question. For instance, on your instruction sheets, you might be given a basic method, like label 4 containers, air, water, salt water, protected. Your job is to take those provided steps and translate them into your own highly detailed logbook entry, making sure to add the specific details of exactly how you executed it in the lab. Section 5, the discussion section. This is the ultimate test. So, you might be wondering, how do you separate an average logbook from a truly fantastic one? Well, the answer lies in fulfilling a very specific checklist of requirements in your discussion, because it's not just about saying what happened, it's about explaining why it happened. A perfect discussion hits all these bases. You describe the results, you identify any possible errors, maybe your stopwatch timing was just a fraction off, or the room temperature changed, and you suggest improvements. Crucially, your logbook has standard questions for this, but you absolutely must also answer the unique, key questions located on your specific experiments worksheet. I literally cannot emphasize this enough. You must inject actual scientific detail into your explanations. If you're doing the reaction rates experiment, you need to be talking about collision theory. If you chose the electrolysis experiment, you've got to explain electron transfer. You have to prove that you grasp the applied chemistry behind the trade. When you look at your actual worksheet right down at the bottom, you'll see a key questions section. Things like, where was energy lost in the system? Or how does this relate to real engines? You are required to research these specific questions and answer them fully within your logbook's discussion space. Every single one of the 8 experiments has a totally unique set of these questions. Do not forget them. Finally, Section 6, Real-World Impact. Why does any of this actually matter? Understanding how an aluminum fitting breaks down when it touches a copper pipe in liquid, which is exactly what you'll see if you choose Experiment 8, isn't just a school task. It's a displacement reaction. And out in the real world, knowing this exact chemistry is what prevents catastrophic material failure in major plumbing systems and electrical grids. A sparky or plumber who doesn't understand metal reactivity, they're a liability. You are learning how to be the expert who gets it right the first time. So as you walk into your double period this week to select your first of 4 trade missions, you have the structure, you know the logbook requirements, and you know the exact standard we're looking for. The only question left is, which real-world problem are you going to solve first?